Hey, what's up, everyone? Welcome to crystal field theory. And crystal field theory is a theory that explains some properties of complex metal ions that can't otherwise be explained using our existing models. And so, in order to understand crystal field theory, you need to understand what a complex metal ion is. And complex metal ions are a compound with a metal ion at the center, and it's surrounded by a number of other molecules or ions. And those other molecules or ions are called ligands. So if we look at what that looks like, we have a copper in the center, that's the metal ion, and it's surrounded by other molecules or ions, in this case the NH3, and those NH3 molecules are the ligands. The bonds between the metal ion and ligands are known as coordinate covalent bonds. And coordinate covalent bonds are bonds in which one atom shares a pair of electrons. So usually in a covalent bond, you have a one-to-one sharing of electrons where one shares one and the other shares one. But in a coordinate covalent bond, one shares both. So the other one is not giving anything and one is just giving both. And this tells us that all ligands are going to function as Lewis bases, because Lewis bases are simply lone pair donators. So in the coordinate covalent bond, the NH3 is going to share two electrons with the copper, and in a sense, it's going to give a lone pair to the copper. And that is exactly what a Lewis base is. They are just lone pair donators, and that makes all ligands function as Lewis bases. Okay, now that we understand what a complex metal ion is, let's take a look at crystal field theory. Crystal field theory assumes an ionic characteristic of the metal ligand bond. So you can see from this terribly drawn diagram that I made, this compound here has 6 ligands around it. And each of these ligands we're going to assume has an ionic characteristic, meaning we're going to assume point charges. So we have negative charges, and they're attracted to this positive ion in the center. You can see a nicer model over here of how that looks. And if we start assuming a ionic characteristic, we can do some interesting things. So if we look at the d orbital of the metal ion in the center, we can see we're going to have those orbitals. But specifically, we're going to have electron repulsion. So the negative charges from the ligands are going to repel the electrons in those d orbitals. But certain d orbitals are going to repel more than others because they are on the same plane that the ligands are on. So if you look at the dz2 orbital, they are on the pole here, and on the top you're going to have the ligand, and on the bottom you're going to have the ligand. And those ligands and the electrons on that orbital are going to have more repulsion than some of the other ones. So in specific, this orbital and this orbital are going to face more repulsion because they are on the poles that the ligands are on. A diagram that shows this very well is this diagram right here. So you can see in these two, the ligands are very close to the orbitals. But in something like here, they are much further away. So what happens is that these ones are going to face more repulsion than these ones. What does this mean for the energy of these d orbitals? So at the beginning, you have all the 5 d orbitals, and they're degenerate, meaning they're going to have the same energy. And you can tell that because they are on the same y-axis. But when you introduce those ligands with that ionic characteristic, what you see is a splitting of the d orbital. So what's going to happen is that the 2 orbitals that face the most repulsion are going to get moved to a higher energy level, while the other 3 that don't face as much repulsion get moved to a lower level. And at this point, it's kind of important to introduce some nomenclature because it's kind of inconvenient to always have to say the dz2 orbital or the dx2 minus y2 orbital. So the orbitals that are moved to a higher energy level are called the Eg orbitals, and then the ones that are moved to a lower one are called the T2G orbitals. So if you hear me referring to those orbitals, then now you know what they mean. We can characterize the energy difference between the Eg orbitals and the T2G orbitals using the octahedral crystal field splitting energy. At this point, it's important to mention that the energy splitting that we see here is characteristic of an octahedral shaped complex metal ion. So other shapes are going to have different splittings, and we'll see that later. But the reason we focus on octahedral is because they're easier to characterize, and their properties are pretty unique. So E naught is important because it tells you the splitting difference, right? So some might have small E naught values and some might have high E naught values. In octahedral crystal fields, the EG goes up 3/5 of E naught. So I don't know if E naught was like 100, the EG orbitals would have a 60 increase. And these are just arbitrary numbers that I'm just using for demonstration. And then similarly, the T2G orbitals go down 2/5 of E naught. So they go down 40. So like I mentioned, based on what ligand you have, you're going to have different splitting energies. You're going to have different E naught values. And so what determines the magnitude of them? Well, we have something called a spectrochemical series. And these are series of experimentally determined sets. So we have determined which ones are going to have the smallest E naught values and which ones are going to have the high E naught values. And they go I, bromine, chlorine, fluorine, hydroxide, water, NH3, carbon monoxide, and then cyanide is going to have the largest. The ones with small E naught values are called weak field ligands, and the ones with large E naught values are called strong field ligands. So let's take a look at how electrons fill up depending on the value of E naught. So for the first three, you're gonna have your electrons, and they're gonna fill up all the orbitals that they want before pairing up. But at this point, you get to a dilemma, right? Will they start doubling up, or will they go on to the higher energy level? So it turns out for low E naught values, they will go to this top value. But for high E naught values, they're gonna double up before going to the higher energy level. A nice analogy to think of it as is like if you were in a bus, and if you had all your empty seats in the way in the back, and you don't want to go that far, so you'll just double up with someone else, right? But if the empty seat was close by, like in the low E naught values, then you're gonna go and sit with yourself. And so these continue to fill up as so. And so as you continue to have more and more electrons in the high E naught values, then they're going to start going to the upper energy levels. And they're gonna double up after those two are filled with one each. And then obviously these ones are going to start doubling up from the bottom, and they are completely filled. And so that's how filling changes based on whether or not you have a small E naught value or a high E naught value. So again, in low E naught values, they will move on to the higher energy level, but in higher E naught values, they're going to start doubling up on the lower ones before moving on to the higher ones. And so like I mentioned, we are dealing with only octahedral ones so far. But there are a bunch more, and let me move this so you can see it better. And you can see some have 3 splitting, some have 4 splitting, and really octahedral ones are the simplest to understand. But there are a bunch more, and all these have interesting properties on their own. And so, like I said, crystal field theory explains some of these interesting properties. And the one I'm going to look at now are going to be colors of solutions. So some transition metal solutions are colored, and it's very hard to explain why without using crystal field theory. If we take a look at like an electron in a hydrogen atom or something, it's moving around and it's in its ground state. And then you introduce some light, some energy, and what happens to that electron is that it gets excited and moves on to a higher energy level. But eventually the electron has to come back down. And when it does go back down to a lower energy level, it emits energy in the form of electromagnetic radiation. Depending on what level the electron goes from and returns to, some of the energy that is emitted might be in the visible light spectrum. And in hydrogen in specific, the series of emissions that cause visible light to be emitted are called the Balmer series. So if a electron is excited to the 3rd energy level and it comes down to the 2nd energy level, a red light is emitted. And then from 4 to 2, you have green light. and then from 5 to 2 you have blue light, and then 6 to 2 you have like purple. You have other series as well, but that light is not as interesting because there is usually UV or some other type of light that we just can't see. So how does this connect back to crystal field theory? Well, consider an electron in the lower energy level. And I'm realizing I didn't put the orbital there, but whatever. Um, so when the electron is in the lower orbital and some light hits it, white light in particular, white light is light that contains all other wavelengths of light. And so when that wavelength hits it, a certain wavelength is going to be the perfect amount of energy to bring the electron from the lower state to the excited state. And so, similar to the hydrogen atom that we saw before, that electron has to come back down. And when it does come back down, it's going to emit the extra energy as light. And so it turns out whatever wavelength of light that you absorbed to bring the electron from the lower state to the higher state, on the color wheel, it's the opposite color that's going to be emitted. So let's say you absorbed a green wavelength. And so what color are you going to see in the solution, or what wavelength of light is going to be emitted? It's going to be a red color. And so fundamentally, that splitting of d orbitals is very similar to like the energy levels that we saw in the hydrogen atom. The electron gets excited, and when it comes back down, it has to emit that energy, and sometimes that energy is in the form of light. One more thing, if a long wavelength is absorbed, then the E naught value is going to be small, but if a short wavelength is absorbed, the E naught value is going to be large. So let's summarize what we learned, right? Crystal field theory is a model for complex ions that assumes an ionic characteristic of the metal ligand bond. So we have those ligands on the top and the metal ion in the center. And because certain d orbitals are very close to the ligands, they face more repulsion than the other three orbitals. And so this results in a splitting of the d orbital to create the Eg orbitals, which are more energetic than the T2g orbitals, which are lower in energy. And things that crystal field theory helps to explain are certain magnetic properties, which I didn't explain, but it also explains colors of certain solutions, which we saw was due to the excitation of an electron and then it coming back down to its ground state or a lower energy level. And that's all I have for crystal field theory. I hope you learned something, and I'll see you later.